Okay, so we're going to break into chapter 13, chemical equilibria. In fact, we're going to cover chemical equilibria. Please understand this chapter. The next three chapters, two chapters, are pretty much exactly the same concept, just applied to acids and bases, solubility, and a couple of other things. So this is actually a pretty important concept. So we're going to talk about this in relation to what kinetics is in just a moment, but these two concepts are kind of, well, they're related, as everything is. So chemical equilibria occurs when a reaction and its reverse reaction proceed at the same time. So we have, this is the best example of kind of how equilibria kind of looks. So we have N2O4, which is colorless, and NO2, which is the brown color. And essentially what you have is, starting with 100% of the N2O4, the reaction immediately starts shifting in the forward direction. There's only direction that it can go. It can only start to produce N2O4. And after a while, we notice that this thing starts to get brown. And it's getting brown because we have produced a bunch of NO2. Now we know the reaction slows down a little bit because kinetics says after you get this massive reaction, things always start to slow down because we have 100% a reactant and it starts to slow down. Well, the forward reaction is still occurring. We're still producing the brown NO2, but there also happens to be a little bit of a reverse reaction occurring. So the reverse reaction starts to occur as well, and two NO2s combined to form N2O4, but it's just slower than the formation of the forward. And eventually what we get to is an equilibrium where we have the forward reaction and the reverse reaction being equal to one another. So at this final state, the forward and reverse reactions, we've come to what we call an equilibrium. So at this point, we have reached an equilibrium. At equilibrium, the concentration no longer change. We produce the same amount of forward and reverse. And the forward is producing the same amount as the reverse is producing, and essentially nothing changes. Nothing looks like it's changing. We do have these molecules shifting back and forth between reaction and product, but eventually it just looks like things are not changing. We can look at this if we look at rate as a function of time. So again, we know the reaction is going to start off very quickly, okay? The gain of NO2 and the loss of N2O4. And of course, because this is a 1-to-2 ratio, this goes much quicker because we produce twice as much just as fast. And what we notice is we reach this point where the rates are in fact equal, okay? So this is the point right here where equilibrium is established. Rate is equal, and equilibrium is established. So rate is equal at equilibrium. Okay, so we've created essentially this equilibrium. We like to say, or what we typically say, is before rates are equal, we have what we call kinetic control. Kinetics are in charge. We still have not reached equilibrium. Kinetics are in control. We are still having changes in reaction rates. And then eventually when they even out and when you have essentially no change in reaction anymore, once we cross that threshold, once equilibrium is achieved, we now say we have thermodynamic control. Thermodynamics takes hold. So kinetics until we reach equilibrium, and at that point it's thermodynamics. So kinetics and thermodynamics are linked through the rate constant, which we're going to look at in just a second. But ultimately, once we reach equilibrium, kinetics no longer plays a part. The kinetics is no longer important. So at equilibrium, the forward and reverse reactions proceed at the same rate. So that's important. They proceed at the same rate. So what that ultimately means is there is no change in concentration. It's change in concentration, right? again, at equilibrium. But it's important to recognize that although there's no change in concentration, we still have those reactions occurring. So reactions are still occurring. Yeah, reactions are still occurring. They just happen to produce the same reactant end product. So equal and opposite, right? So I'm producing the same amount of product as I am reactant, and as a result, nothing looks like it's changing. The concentrations remain constant, okay? So yeah, so that's the idea behind equilibrium. So now we're going to break into equilibrium constants. We're going to start to study this more. Instead of looking at reaction rate as a function of time, we're going to look at concentration as a function of time. Remember, we have kinetic control here, right? Concentrations start changing rapidly until we reach that equilibrium where they stop changing altogether, because then we've reached thermodynamic control. And now we have reached what we call a steady state. The steady state is again, it's like the bathtub model where I'm putting the same amount in as it's coming out. So the reaction is happening the same in the forward and reverse. So we have the same rate of forward and reverse reaction. The rate is the same. Rate is equal to one another. Not rate constant, rate is equivalent. Okay, that's important. Rate is equal, not rate constant. Again, there is no delta, there's no change in concentration. Okay, good. So if rate is equal, let's think about what this actually means. So let's depict this equilibrium. So there's a new way that we're going to begin writing this. So I have N2O4 as a gas. The forward process, I'm going to have K1, or yeah, K1 in one direction. It's going to produce 2 NO2 gas. But of course, I also have the reverse reaction occurring as well, giving me K minus 1. K minus 1 meaning we're going in the reverse direction. So equilibrium constant, or I'm sorry, kinetic constant, rate constant of the forward, rate constant of the reverse. We can write this out as rate of the forward reaction is equal to K1 concentration of N2O4. And rate of the reverse is rate equals K minus 1 concentration of NO2 squared. Great. So what that means is if we look at the forward and reverse reaction, the forward reaction N2O4 as a gas is 2 NO2 as a gas. Again, the rate of the forward. Actually, I already did all this, so I'm just not going to do it down here. So we have these two equations, rate of the forward, rate of the reverse. Right. Rate of the forward, rate of the reverse. All right, great. So what do we do with that? Well, therefore, at equilibrium, we can imagine what we have is if these are equal to one another at equilibrium, what we know is it turns out that rate of the forward equals rate of the reverse. Again, this is all at equilibrium, right? So at equilibrium, rate of the forward equals rate of the reverse, which ultimately means that these two things are equal to one another. So at equilibrium, that happens to be true. K1 is equal to, in fact, let me just change these. It's no longer K1. We could say KF forward is equal to K minus 1, which happens to be K of the reverse. Okay. So I'm going to rearrange this. So now I'm going to rearrange this, and instead I'm going to have Kf over Kr, or reverse, is equal to concentration of NO2 squared over concentration of N2O4. Again, just some algebra cross multiplying, or just divide by Kr and concentration of NO2. The thing that I want to point out here is on top, I have reactants. And on the bottom, I'm sorry, I have products. On the top, I have products. And the bottom, I have reactants. Okay. And that's it. This is the final idea. Kf over Kr is equal to concentration of NO2 squared over concentration of N2O4. Again, this is products. Oop, what's going on there? Over reactants. And this little Kf term over Kr term actually becomes capital K EQ, which is now what we know as the equilibrium constant. So that's the takeaway. KEQ, the equilibrium constant, capital K, which is a combination of the forward over the reverse reaction, is equal to products over reactants. That's it. That's the end of the story. So generalizing this, being able to come up with any equilibrium. So first of all, an equilibrium expression is going to come from a balanced chemical equation. So this time we actually are going to use a balanced chemical equation. AA plus BB is in equilibrium with CC plus D. D, what we know now, or what we can write, is the following. Again, this is the K. We're going to do KC, which is going to stand for the equilibrium of concentrations, is equal to concentration of products over the concentration of reactants, which is equal to, and then to do it properly from the balanced chemical equation, my products, concentration of C, capital C raised to lowercase c, concentration of capital D to lowercase d. So again, that's coefficient in front. Concentration of A, concentration of B. Products over reactants, okay? So what do we know? How can we finalize this? This is the equilibrium constant. Equilibrium constant in this K is Kc, so it's concentration. We're going to also have a Kp, which is actually for gases, which is going to be in pressure. And now it's important to talk about all of the other ones that we have. So we have Kp, we have Kc. So those are two different ones. Everything else is pretty much in concentration at this point. So Ka is the dissociation of an acid. Kb is the dissociation of a base. Ksp, solubility product, is having to do with the dissolving of a product. Kf is the formation of a complex. Kw has to do with the autoionization of water. So there's plenty more. So doesn't matter which K you're talking about. They are all going to have this arrangement. So if you have a K, all you have to do is simply write this down every single time. Products over reactants. There are certain little things you kind of have to understand, but it's all going to behave exactly like this. So don't get it like twisted. This is exactly what you need to focus on. If you know this, you're fine. If you keep remembering this, you're fine for like the rest of the next 3 chapters, this one and the next 2. Okay. So equilibrium constants at constant pressure. So Kp is slightly different than Kp is slightly different than Kc. So let's take a look at the generic version of gas law. So concentration of A gas, A times A, yep, B times B, or coefficient B, gas B plus C. Instead of concentrations in my equilibrium constant, Kp is going to be equal to the pressure of the products. So the pressure of B raised to B, actually I'll just put that in parentheses, raised to B times the pressure of A raised to A, all over the pressure of C, or I'm sorry, I'm messing this up. So pressure of C raised to the C, pressure of A raised to the A. So products over reactants. It was just going on autopilot there. Okay, so that's it, Kp or Kc. So if you have something that's in aqueous form, it's Kc. If you have something that's gaseous form, it's going to be Kp. So let's take a look at these 3. Let's write these examples. I want to change one. This is actually supposed to be a aqueous. So write the equilibrium constants for these 3 reactions, okay? All right, good. So the relationship between Kc and Kp. I'm going to go through the derivation really quickly. You can ignore me for the next couple of minutes and actually just skip ahead to the equation if you like. So we know that PV equals nRT. Again, it all derives from there. So pressure is equal to nRT all over V, knowing that R is 0.08206. And actually, we're just going to skip to it anyway. So this is the equation you need to know. Kp is equal to Kc RT raised to delta N. And we can actually plug that in. And the delta N is the number of moles of gaseous reactant, gaseous product minus moles of gaseous reactant. So if I had a reaction of, we'll use the original one, N2O4 as a gas is in equilibrium with 2NO2. The delta N for this, so I have 1 mole of gas and I have 2 moles of gas. So delta N is 2 moles minus 1 mole equals 1 mole. And ultimately, you're just multiplying by RT. Okay. If there's 0, this term is going to go away. And it is possible to have negative numbers, which is going to change things around a little bit. But that's the relationship. Kp is equal to Kc RT delta N. So that's how you do that calculation. So we skip the derivation, which is great. Convert this Kc into a Kp. That's what we're going to do there. Give that a go, and we'll do that in class. All right, so we have created this conversation about, we have developed the idea of K, but what does it actually mean? Again, we do know that capital K is equal to the concentration of products over the concentration of reactants. Okay, products over reactants. What does the value mean? Well, let's think about that. So when K is much, much greater than 1, we always want to think about the extremes. Let's think of when K is gigantic. K can be a very small number, or K can be 0, or K can be a really large, like an infinite number. Okay, right? If I have 100% products and this is 0, it's undefined or it's very large, right? We're always going to have some reactants, so we're never going to actually have an undefined number. So if I have 100% of this and close to 0 of this, the number is very, very large, like my first example. If reactants are very large and products are non-existent, we have almost close to 0 as the number, right? So if K is very, very large, what that tells us is, therefore, K is equal to a very high concentration of products. That number is very large. And the concentration of reactants is very, very low, right? So another way of looking at it pictorially is my reactants are low and my concentration of products is high. What we would say is this thing is going to be product favored. This is going to be product favored, okay? Because there is so many products, right? The equilibrium favors the products. And again, we have to remember this is not like a moment in time that we have to pause. If we let a reaction run and it has a really high K value, it's always going to be product favored, right? Okay. We also would say something along the lines of the equilibrium lies to the right, meaning it lies to the right, it lies to the product side. We have equilibrium on the right. What happens if we have a situation where when K is much, much less than 1, so very close to 0, right? The opposite is going to be true. K is going to have a very small number on the top and a very large number on the bottom. And therefore, we are going to have a ton of reactants on almost no products. And if that's the case, we call this reactant favored, or equilibrium lies to the left. Okay, good. So again, it gives you an idea of what these numbers mean, and we're going to see these. So really high value. And then I just want to reiterate, when K is really, really large, we have some K values that are like, I don't know, some number times 10 to the 34. Like that's massive. That's a huge number. And we have some numbers like 1 times 10 to the negative 45. That's a number for a really small K. So these are really tiny, really, really minuscule numbers. Okay. So yeah, so that's how we have to understand those values of K. And all right, so that's what the K value of K means. We can manipulate K values because remember, it's based on a balanced chemical equation. So if I have a balanced chemical equation, if I alter that equation, it is going to alter the equilibrium constant. So let's give that a go. So if I have N2O4 is in equilibrium with 2NO2, okay, let's say that Kc is equal to, again, equilibrium concentration of products over concentration of reactants, products over reactants. That happens to equal 0.212 at 100 degrees Celsius. So at 100 degrees Celsius. Temperature is important because temperature is going to change the equilibrium, the rate constant changes the equilibrium constant. So is this product or reactant favored? 0.212 is the value. This is reactant favored, right? It's a very, I'm sorry, yeah, it's reactant favored because it's a small number. The smaller the number, the more reactant favored it is. If K is equal to 1, what's the ratio of products to reactants? It means equal number on the top and on the bottom, so it's a 50-50. It's 50% of each, right? So 212 means we have about 80% of its reactants, 20% of its products, or something like that. Anyway, so this is what I have for my Kc. If I reverse the direction of the reaction, so if I reverse it, by reversing the reaction, I now have NO2 to N2O4. Well, my new Kc is equal to products, which is N2O4 this time, all over the concentration of NO2 squared. So instead of, I reverse the direction, notice what happened. Notice what happened with these two, right? Now I have essentially just flipped them upside down. So if I flip them upside down, my new K value is simply 1 over 0.212, or in this case, 4.72. But so by reversing the reaction, K, we take it becomes the reciprocal of K. So Kc becomes 1 over Kc. Okay, so there we go. That's the change. So if I reverse the direction of a reaction, K is going to be the reciprocal because I flip the K value. Again, it's based on the balanced chemical equation. Okay. All right, good. So the other manipulation that you can have is, again, if I start with N2O4 in equilibrium with 2NO2. Again, these are in gases, but we're using concentration, doesn't matter. Kc is equal to concentration of NO2 squared, products, over concentration of N2O4 over reactants. So equals 0.212 at 100 degrees Celsius. So now the question is, what happens when I multiply by some value, let's say n. So in this case, I'm just going to multiply by 2. So 2 is equal to n for me. So if I multiply this whole thing by 2, what I end up with is 2N2O4 in equilibrium with, those terrible arrows, equilibrium with 4NO2. My Kc is now equal to the concentration of NO2 squared raised to the 4th, all over the concentration of N2O4 raised to the 2nd. What I have done there is I've essentially just squared both of them. So 212 squared. So multiply by n is equivalent to raising Kc to Kc raised to that n. Okay, so that is the manipulation. If I multiply by n, I end up basically just raising the new Kc, the new equilibrium expression to 2 or to n, whatever that happens to be. Okay. Okay. So again, these are basics, and we're going to use this in a number of different ways. But equilibrium constants are going to act a lot like Hess's law will. Do you remember Hess's law where we combined different steps together? So for this, I want you to think Hess's law. It's going to help you hopefully get through this. So let's consider a reaction. So if I have A plus B is in equilibrium with C, we have some K value for this, K1. And then I have C plus F is in equilibrium with G plus A. And this is my K2, capital K, right? Capital K2. The new reaction that I'm creating, let's just think of what cancels. I lose C, I lose A. So my resulting reaction is B plus F is in equilibrium with G. My new K, K3, is equal to simply K1 times K2. And I can actually show you that if you wrote those out, you would see that they would cancel out, right? So if it's reactants here and it's products here, they would cancel because they're going to be on the opposite side of the fraction. Same thing with C if we multiply those out, because K, in this case, K1 is equal to the concentration of C over the concentration of A times the concentration of B. And K2 is the concentration of G times concentration of A all over concentration of C times concentration of F. So if I multiply those two, they're going to cancel out and give me my new K3, which is basically just missing those two. Concentration of G over BF. Okay, makes sense? Great. All right, actually, let's just do it. Concentration of C, concentration of A, concentration of B, times, and then it's just basically continuing, concentration of G, concentration of A, concentration of C, concentration of F. So we know that C is on top and the bottom, that goes to 1. A is on the top and the bottom, that goes to 2, or that cancels as well. So we're left with G over B F, and that's exactly what we'd expect for that reaction for K3. Good? Okay. All right, just a little bit more. I think we're almost there. Yeah, we're almost where we need to be. Heterogeneous equilibria. So we have two types of equilibrium. We have homogeneous and heterogeneous. So in homogeneous equilibria, all reactant and product are in the same phase. So here we have gases for both of them. So we'd say, all right, well, I can actually write this as a Kp, right? I can write this Kp is equal to concentration of NO2 squared all over concentration of N2O4 done, or that's a Kc, isn't it? Yep, Kc. My Kp would be pressure of NO2 squared over pressure of N2O4. And there we go, there's my Kp. You can write Kc because remember, we can convert between the two. Heterogeneous equilibria is portions are in different phases. So portions are in, let's spell properly, there we go. Portions of reaction are in different phases. Okay, so portions of the reaction are different phases. So if we want to write the equilibrium constant for this, we would say, all right, Kc is equal to my products, lead 2+, chloride squared all over my reactants, which is lead chloride. There we go. The only problem is what ends up happening is anything that is not aqueous, so anything in, I guess I should say, in liquid and or solid state equals 1. They do not appear in equilibrium. Okay, so that's an important part. Anything in liquid or solid is equal to 1, and they just go away. So in this case, lead chloride is solid. I'm going to eliminate that, and so I'm going to rewrite my Kc. My Kc is equal to lead 2+ times Cl minus squared. There we go. This is the correct equilibrium constant. So anytime you see a liquid or you see a solid, just don't write it, and your equilibrium will be just fine. In fact, you don't even know whether need to know whether it's heterogeneous or homogeneous. Just simply don't write liquids or solids, only aqueous and gases. Okay. All right. Yep. And that's essentially it. I don't know why I wrote that other than that's the same exact thing anyway. So therefore, those do not appear. So we're going to get into equilibrium calculations. Your book, we're skipping through 13.3 because I put Le Chatelier's principle at the end. So we're going to look at a bunch of equilibrium concentration calculations, and then we're going to go to Le Chatelier's principle because I want you to understand how to calculate these before we get there. This stuff is actually fun in terms of it can be a little frustrating, but you can really nail it down. So that's it.